Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 8, Carboxylic Acids. Carboxylic acids with both carbonyl and hydroxyl groups are some of the most reactive organic molecules you'll encounter on test day. As we will see in this chapter, these molecules can react as acids, as their name suggests, nucleophiles, and electrophiles, and are integral to many biological processes. Carboxylic acids are found in soaps, oils, preservatives, skincare products, clothing, and most importantly for the MCAT, amino acids. Carboxylic acids often have strong, unpleasant odors. For example, acetic acid, or ethanoic acid, is the main ingredient in vinegar. Propionic acid, or propanoic acid, gives Swiss cheese its smell. Butyric acid, or butanoic acid, is found in rancid butter and body odor. So what makes carboxylic acids so interesting and versatile? First, they're acids, so they like to give away protons, particularly because when they do so, the remaining negative charge resonates between two oxygen atoms, making the anion very stable. This makes carboxylic acids some of the most acidic compounds encountered in organic chemistry, with pKa values between 3 and 6. Compare this with alcohols, which have an average pKa around 17. Carboxylic acids are also excellent at hydrogen bonding, which results in large intermolecular forces and high boiling points. Finally, carboxylic acids are ubiquitous in nature and are synthesized by all living organisms. Description and properties. A carboxylic acid contains both a carbonyl group and a hydroxyl group bonded to the same carbon with 3 bonds to oxygen atoms. This is one of the most oxidized functional groups encountered in organic chemistry. Carboxylic acids are always terminal groups. Nomenclature. In the IUPAC system of nomenclature, carboxylic acids are named by adding the suffix oic acid to the parent root when the carboxylic acid is the highest priority functional group. When this is true, the carbonyl carbon becomes carbon number 1. Figure 8.1 shows 2 examples. Methylpentanoic acid and isopropyl oxohexanoic acid. 4 isopropyl, 5 oxohexanoic acid. Like the other functional groups, many carboxylic acids are also named by their common names. Make note of the common prefix used in the example in figure 8.2. 8.2 we have methanoic acid or formic acid, ethanoic acid or acetic acid, and propanoic acid or propionic acid, which is a propane molecule with 2 oxygens and an OH on the first carbon. Let's write down just the suffix, oic acid. Let's draw these molecules just because I bet we're going to have to use them. One, two, three. Propanoic. Methanoic or formic. Ethanoic or acetic, and propanoic or propionic acid. Carboxylic acids, cyclic carboxylic acids, are named by listing the cycloalkane with the suffix carboxylic acid. Cyclic carboxylic acid. Salts of carboxylic acids are named beginning with the cation followed by the name of the acid with the ending -ate, replacing oic acid. Typical examples are shown in figure 8.3. So here we have chloromethylcyclopentane carboxylic acid and sodium hexanoate. So what's it write down? 08. Instead of oic acid. For salts, finally, dicarboxylic acids, which have a carboxylic acid group on each end of the molecule, are common in biological systems. The smallest dicarboxylic acid is oxalic acid with 2 carbons. The next 5 straight chain dicarboxylic acids are malonic, succinic, glutaric, adipic, and pimelic acids. Their IUPAC names have the suffix dioic acid, ethane dioic acid, propane dioic acid, butane dioic acid, pentane dioic acid, hexane dioic acid, and heptane dioic acid. Figure 8.4 shows several examples, and they show an example of ethane dioic acid or oxalic acid, propane dioic acid or malonic acid, and butane dioic acid or succinic acid. So let's write down dicarboxylic acids are named with the suffix dioic acid. Got 08 for salts. Starting with oxalic acid or ethane dioic acid. Malonic acid is propane dioic acid, and succinic acid is butane dioic acid. And let's draw these out. You take ethane and put a carboxylic acid on each side. Propane is 1, 2, 3 with carboxylic acids on the end. And then butane. 1, 2, 3, 4. With a carboxylic acid on each side. All right. What else do they give us? Pentane dioic acid, hexane dioic acid, heptane dioic acid. I guess we can figure out what those look like, can't we? Physical properties. Many of the physical properties of carboxylic acids are similar to those of aldehydes and ketones because they both contain carbonyl groups. However, the additional hydroxyl group permits carboxylic acids to hydrogen bond and provides another acidic hydrogen that can participate in reactions. Hydrogen bonding. Carboxylic acids are polar because they contain a carbonyl group and can also form hydrogen bonds because they contain a hydrogen bonded to a very electronegative atom, in this case, the hydroxyl oxygen. Carboxylic acids display particularly strong intramolecular attractions because both the hydroxyl oxygen and carbonyl oxygen can participate in hydrogen bonding. As a result, carboxylic acids tend to form dimers, pairs of molecules connected by two hydrogen bonds. Multiple hydrogen bonds elevate the boiling point and melting points of carboxylic acids past those of corresponding alcohols. Boiling points also increase with increasing molecular weight. Acidity. So let's write down high boiling point. Acidity. The hydroxyl hydrogen of a carboxylic acid is quite acidic. This results in a negative charge that remains after the hydrogen is removed, and resonance stabilization occurs between both of the electronegative oxygen atoms. Delocalization of the negative charge results in a very stable carboxylate anion, which is demonstrated in figure 8.5. Let us draw this resonance-stabilized structure, a carboxylate anion stability. The negative charge from deprotonation is stabilized through resonance. So between the two oxygen atoms, the double bond going back and forth is the resonance. All right. The more stable the conjugate base is, the easier it is for the proton to leave, and thus the stronger the acid. Carboxylic acids are relatively acidic, with pKa values on the order of 4.8 for ethanoic acid and 4.9 for propionic acid. However, keep in mind that although these are quite acidic for organic compounds, they do not compare to strong acids like HCl with a pKa of negative 8.0 or even HSO4, hydrogen sulfate, sulfuric acid with a pKa of 1.9. Remember, lower pKa values indicate stronger acids. Substituents on carbon atoms near a carboxyl group influence anion stability and therefore affect acidity. Groups like NO2 or halides are electron withdrawing and increase acidity. In contrast, NH2 or OCH3 are electron donating groups that destabilize the negative charge, decreasing the acidity of the compound. The closer the substituents are to the carboxyl group, the greater the effect will be. So let's write down that NO2 halides are electron withdrawing, and so they increase acidity, whereas functional groups like an H2 or OCH3 are electron donating and decrease acidity. In dicarboxylic acids, each COOH group influences the other COOH group. Carboxylic acids are electron withdrawing due to the electronegative oxygen atom they contain. The net result is that dicarboxylic acids are more acidic than the analogous monocarboxylic acids. However, when one proton is removed from the molecule, the carboxylate anion is formed, resulting in an immediate decrease in the acidity of the remaining carboxylic acid. This makes sense because if the second group were deprotonated, it would create a doubly charged species with two negative charges repelling each other. Due to this instability, the second proton is usually less acidic, harder to remove than the analogous proton of a monocarboxylic acid. Beta dicarboxylic acids are dicarboxylic acids in which each carboxylic acid is positioned on the beta carbon of the other. In other words, there are two carboxylic acids separated by a single carbon. These compounds are notable for the high acidity of the alpha hydrogens located on the carbon between the two carboxylic groups, or between the two carboxyl groups, with a pKa of around 9 to 14. Loss of this acidic hydrogen atom produces a carbanion, which is stabilized by the electron withdrawing effect of both carboxyl groups, as shown in figure 8.6. So let's write down second so let's write down that the pKa of a dicarboxylic acid of a COOH times 2, pK of 2 COOHs, this looks like an A, is less than pKa of just 1. And we don't need DR. Dicarboxylic acids and beta is even more. Let's move this over and put beta COOH, the pKa of beta COOH is even lower. Should we draw the resonance stabilization of beta dicarboxylic acids? We have our original molecule with carboxylic acids 1 carbon apart. And in one of the structures, we have double bonds between the oxygen and their respective carbon. And in the alternate structures, we have a double bond between two of the carbons. All right. Acidity of the alpha hydrogen in beta dicarboxylic acids. Note that the alpha hydrogen is less acidic than the hydroxyl hydrogens. The hydroxyl groups are left protonated in this example for demonstration purposes only. So these hydroxyl hydrogens would go first. So this is not true to real world. All right. Note that this also applies to the alpha hydrogens in a beta diketone. Beta ketoic acids, beta dialdehydes, and other molecules that share the 1,3 dicarbonyl structure shown in figure 8.7. 1,3 dicarbonyl compounds have, like beta diketones, beta ketoic or keto acids, and beta dialdehydes. General structure: 2 carbonyl bonds separated by 1 carbon. All right. What causes a relatively high acidity of carboxylic acids? The high acidity is due to the electron withdrawing oxygen, stabilizing the structure after it's lost its hydrogen. Between a monocarboxylic acid, a dicarboxylic acid, and a dicarboxylic acid that has been deprotonated once, which will be the most acidic. The dicarboxylic acid that has all of its protons is the most acidic, followed by the monocarboxylic acid, followed by the dicarboxylic acid that's already been once protonated. The dicarboxylic acid, after it's been once protonated, is not so acidic. All right. Reactions of carboxylic acids. The properties of carboxylic acids make them highly reactive in a number of different categories. Several of the most important reactions are described here.
Composition updating.
Whoops.
Playing from iPhone 2.
All right. Synthesis of carboxylic acids. As described in earlier chapters, carboxylic acids can be prepared via oxidation of aldehydes and primary alcohols. The oxidant is often a dichromate salt, like potassium or sodium dichromate, chromium trioxide, CrO3, or potassium permanganate, KMnO4. as shown in figure 8.8, but several other oxidizing agents also can work. Remember that secondary and tertiary alcohols cannot be oxidized to carboxylic acids because they already have at least 2 bonds to other carbons. So this is only the terminal groups. Oxidants include Na2Cr2O7, K2Cr2O7, CrO3, KMNO4. Let's write down that this is synthesis. And the basic oxidation of a primary alcohol looks like this. KMNO4 added to ethanol makes the trivial formic acid. Is that formic acid? Ethanoic, which is acetic acid rather. All right. There are many other methods of generating carboxylic acids, including organometallic reagents, Grignard, reagents, and hydrolysis of nitriles, CN. But these are outside the scope of the MCAT. Let's write them down just for kicks. Grignard reagents, hydrolysis of nitriles. All right. Nucleophilic acyl substitution. Many of the reactions in which carboxylic acids and their derivatives participate proceed via a single mechanism, nucleophilic acyl substitution. This mechanism is similar to nucleophilic addition to an aldehyde or ketone, which was discussed in chapters 6 and 7. The key difference, however, focuses on the existence of a leaving group in carboxylic acids and their derivatives. In this case, after opening the carbonyl via nucleophilic attack and forming a tetrahedral intermediate, the carbonyl can reform, thereby kicking off the leaving group. This reaction is shown in figure 8.9, nucleophilic acyl substitution. Step 1 is the nucleophilic addition. Step 2, elimination of the leaving group and reformation of the carbonyl. Let's call this nucleophilic acyl substitution. Involves an addition step and an elimination step. Here we have the nucleophile. Attacking the carbonyl carbon. We have the carbonyl opening up. We have the carbanion, or the, sorry, not the carbanion. We have a intermediate, and then we have the negatively charged oxygen atom attacking the carbon and the leaving group leaving, which is the OH grabs a hydrogen to make H2O, and that makes a good leaving group. So this attacks, this leaves. All right. In these reactions, a nucleophilic molecule replaces the leaving group of an acyl derivative. Acyl derivatives encompass all molecules with a carboxylic acid-derived carbonyl, including carboxylic acids, amides, esters, anhydrides, and others. These reactions are favored by a good leaving group. Remember, weak bases, which are often the conjugate base of strong acids, make good leaving groups. These reactions are also favored in either acidic or basic conditions, which can alter the reactivity of the electrophile and nucleophile. What exactly does acyl mean? Acyl means a radical of general formula COR. So acyl just means having a carbonyl. So what's the difference between carbonyl and acyl? An acyl group generally refers to a carbon group derived from a carboxylic acid, whereas a carbonyl group is a more general functional group with a carbon double bonded to an oxygen. So in one case, there's an R group. In another case, it's ambiguous whether there is a R, whether there's a carbon next to it or something else. So I guess if I were to draw it out to you, carbonyl refers to this with any A and B, whereas acyl refers to specifically another carbon. I guess this could be like an OH, or it could just be an H, like in aldehydes. All right. Acyl derivatives, including esters, anhydrides, etc., they're favored by a good leaving group. Weak bases make good leaving groups. Next, amides. Let's write down that weak bases make good leaving groups. Weak bases make good leaving groups. All right, amides. Carboxylic acids can be converted into amides if the incoming nucleophile is ammonia or an amine. As shown in figure 8.10, this can be carried out in either an acidic or basic solution to drive the reaction forward. So let's draw a carboxylic acid here with the OH, the hydroxyl group in blue, and a nitrogen bonded to an R group and two hydrogens. And we have the hydrogen here in blue to kind of show you what's going to happen. We're going to lose an H2O in the process, it seems. And we're left with a nitrogen bonded to a carbonyl and R groups on the side. All right. Amides are named by replacing the oic acid suffix with amide. Amide. In the name of the parent carboxylic acid, any alkyl groups on the nitrogen are placed at the beginning of the name with the prefix N. Amides exist in a resonance state where delocalization of electrons occurs between the oxygen and nitrogen atoms, as shown in figure 8.11. Alkyl groups on the nitrogen get an N. Amides, let's look at the resonance of amides, resonance between the carbonyl and lone pair on the nitrogen, stabilizes this bond and restricts its motion. Let's draw this resonance. Might as well. All right. And we just have the double bond moving between the oxygen in the carbon and the carbon in the nitrogen, and there being a negative charge on the oxygen, because oxygen can do that. All right, amides that are cyclic are called lactams and are named by replacing oic acid with lactam, Lactam. Cyclic. They may also be named by indicating the specific carbon that is bonded during cyclization of the compound. Several examples are shown in figure 8.12. We have beta-lactam, gamma-lactam, delta-lactam, epsilon-lactam. Interesting. Should we draw these? We're going to draw these just to have the practice of drawing molecules. Beta-lactam is a square. Gamma-lactam is a pentagon. delta lactam is a hexagon. And epsilon lactam, I guess, is a heptagon? 1, 2, 3, 4, 5, 6, 7. 7 sides. All right. How many of you guys are good at drawing heptagons? I'm just going to write in beta, gamma, delta, epsilon. My gamma looks like a Y. Not anymore. Lactam. All right, esters. Esters are a hybrid between a carboxylic acid and an ether, ROR, which can be made by reacting carboxylic acids with alcohols under acidic conditions. As shown in Figure 8.13, esterification is a condensation reaction with water as a side product. In acidic solutions, the carbonyl oxygen can be protonated, which enhances the polarity of the bond, thereby replacing additional positive charge on the carbonyl carbon and increasing its susceptibility to nucleophilic attack. This condensation reaction occurs most rapidly with primary alcohols. So I guess less steric hindrance. So let's write down esterification. Let's write down that it's a condensation with water as a side product. Does that mean that it's a hydration? What do they call that? Dehydration? Condensation? Because the molecule lost its water. Dehydration. Condensation / dehydration. Let's look at an esterification reaction of carboxylic acid with an alcohol. We have the acid being attacked by the alcohol. We have an intermediate, and then we have water leaving to make an ester. Let's draw this mechanism. We got the acid, we got the alcohol, we got the intermediate with a positive charge on the oxygen. And then I guess we'll have to lose the hydrogen to lose the positive charge. So because there's a positive charge on the oxygen, hydrogen just leaves. So the hydrogen that's on the oxygen moves around to the acyl oxygen, or the carboxylic acid's oxygen, and turns it into H2O, which makes a good leaving group. All right. Draw some arrows in here. Let's draw some red arrows for the nucleophile attack to the carbonyl carbon, the opening of the carbonyl, and then we have shuffling around of the hydrogen. So I see why they put a little tilde instead of a negative, because it's not just losing hydrogen, it's just kind of reshuffling, it's moving around. And then we have hydrogen leaving, water leaving, so what we have here is a bond to oxygen turning into a double bond and a positive charge. All right. Lots of charges to follow around here. Esters are named in the same manner as salts of carboxylic acids. For example, the ester shown in the reaction in figure 8.13 has the common name ethyl acetate, or the IUPAC name ethyl ethanoate. Let's write that down at the bottom. This is ethyl acetate, or also named ethyl ethanoate. Esters that are cyclic are called lactones and are named by replacing oic acid with lactone. Several examples are shown in 8.14. And let's draw some of these just for the practice. We have acetolactone. Acetolactone looks like a triangle with one of the carbons replaced with an oxygen and then a double bond on another carbon. We have beta-propiolactone, which is like a square with a double bond to an oxygen and one of the carbons replaced with an oxygen. We have butyrolactone, which looks like a pentagon. And we have valerolactone, which looks like a hexagon. All right. Anhydrides. Anhydrides can be formed by the condensation of two carboxylic acids. They are named by replacing the acid at the end of the name of the parent carboxylic acid with anhydride, whether cyclic or linear. One example is the condensation of two molecules of ethanoic acid to form ethanoic anhydride. As shown in figure 8.14, just like the above reactions, anhydride formation occurs via nucleophilic acyl substitution. So lactams are cyclic amides. Lactones are cyclic esters. All right. Anhydrides Let's draw the synthesis of an anhydride via carboxylic acid condensation. So let's just write down that this is also nucleophilic acyl substitution. It is condensation. And therefore it is also, and because it's water, it's also dehydration. All of the above. And we have two carboxylic acids losing water and joining at the oxygen that lost a hydrogen. So I want to write all the carbons in. I'm just going to draw it in the form we're kind of used to. Carboxylic acid, carboxylic acid, and afterwards they are joined and this is ethanoic anhydride. Anhydride just means it's derived by dehydration. All right, reduction. Carboxylic acids can be reduced to primary alcohols by use of lithium aluminum hydride, LiAlH4. Aldehyde intermediates may be formed in the course of this reaction, but they too will be reduced to the alcohol. This reaction occurs by nucleophilic addition of hydride to the carbonyl group. The reaction mechanism is shown in figure 8.16. We have the carboxylic acid being attacked by the hydrogen. We have the carbonyl opening up And then we have OH hydroxide ion leaving, making a aldehyde. And then we have a second attack of another hydrogen, another carbonyl opening, and then we're left with an alcohol. Reduction by LiAlH4. And we have the diagram of the acid being attacked by hydrogen. We have the carbonyl opening. And then we have hydroxide leaving us with an aldehyde. And then we have a second attack. And that process kind of happens over again. Leaving us with an alcohol. Let's draw some red arrows for the hydrogen attacking the carbonyl carbon, the carbonyl opening up, and then the negative oxygen reverting back into a double bond and hydroxide leaving. And then that happens again. And then I guess the oxygen is protonated. They don't show that. But the negatively charged oxygen atom is going to be protonated at the end to make the alcohol. We have the acid. We have the aldehyde. Finally, the alcohol. I'm sure you'll need 2 moles of hydrogen to do this reaction. Lithium aluminum hydride is a strong reducing agent that can successfully reduce a carboxylic acid. A gentler reducing agent like sodium borohydride, NaBH4, is not strong enough to reduce carboxylic acids at all, not even to aldehydes. So let's just write NaBH4 does not work. All right. Next, decarboxylation. Decarboxylation describes the complete loss of the carbonyl group as carbon dioxide. This is a common way of getting rid of carbon from the parent chain. 1,3-dicarboxylic acids and other beta-keto acids may spontaneously decarboxylate when heated. Under these conditions, the carboxyl group is lost and replaced with hydrogen. Because both the electrophile and nucleophile are in the same molecule, the reaction proceeds through a 6-membered ring in its transition state. As shown in figure 8.17, the enol that is initially formed from the destruction of the ring tautomerizes to the more stable keto form. So let us draw this structure. So we have a dicarboxylic acid. Or I guess it's a keto acid. This one, in this case, it's not carboxylic, it's a ketone and a carboxylic acid. So a keto acid. Then in the next step, we have the double bond, the carbonyl electrons attacking the hydrogen on the carboxylic acid. We have that bond, those electrons going and making a double bond with the carbonyl carbon, the carboxylic acid's carbonyl carbon. And then we have the bond between the carboxylic acid and the central carbon, the 2-carbon, breaking, and those electrons going into this enol formation. So let's draw all those out. Some red arrows to show the carbonyl attacking the hydrogen. That bond going into a double bond with carbon. And this bond breaking. Alright, I guess that'll do it. Decarboxylation of carboxylic acids, loss of CO2. The intramolecular reaction proceeds via a 6-membered ring transition state, and the product tautomerizes from the enol to the more stable keto form. Alright. Next, saponification. When long-chain carboxylic acids react with sodium or potassium hydroxide, a salt is formed. This process, called saponification, occurs by mixing fatty acids with lye, sodium or potassium hydroxide, resulting in the formation of a salt that we know as soap. Soaps can solvate nonpolar organic compounds in aqueous solutions because they contain both a nonpolar tail and a polar carboxylate head, as shown in figure 8.18. So we have carboxylic acid salt, or soap. We have this long chain, carbon chain for a tail. And then we have the polar carboxylic acid head. And they also have sodium here as a salt. When placed in aqueous solution, soap molecules arrange themselves into spherical structures called micelles, as shown in figure 819. The polar heads face outward, where they can be solvated by water, and the nonpolar hydrocarbon chains are oriented toward the inside of the sphere, protected from the solvent. Nonpolar molecules, such as grease, dissolved in the hydrocarbon interior of the spherical micelle. The micelle is as a whole then dissolves in water due to the polarity of its exterior surface. We have a picture of the soap micelle. The polar heads interact with the hydrophilic environment. The nonpolar tails are oriented toward the interior of the micelle. So the aqueous is on the outside, organic on the inside. Should we draw some of these? Carboxylic acid head, alkane tail. And let's just draw a few of these so you could see what a micelle might look like. I'm going to draw this again to make them come in towards the center a little bit more. Not touching. No touching. All right, you get the idea. This is your micelle. All right. Before you move on, for each of the derivatives below, list the nucleophile used to form the derivative in an acyl substitution reaction and the name of the cyclic form of that functional group. So, carboxyl acid derivative of an amide formed by reaction with, what, NO2? Or NH3, rather. The nucleophile used is nitrogen, right? Nitrogen or ammonia is what they're going for, I guess. An amide, a nitrogen, the name of the cyclic form is a lactam. An ester is made with an alcohol in a carboxylic acid. The name of the cyclic form is lactone. An anhydride is made with two carboxylic acids, and it's the name of the cyclic form of an anhydride is no different. Briefly describe the mechanism of nucleophilic acyl substitution reactions. Nucleophilic acyl substitution. A nucleophile attacks and the carbonyl opens up. And then the negatively charged, making a a complex, and then the negatively charged oxygen goes back and attacks the carbon again, and water leaves as a leaving group, or something leaves as a leaving group. Can carboxylic acids be reduced by sodium borohydride? No, because you told us so. Under what conditions will a carboxylic acid spontaneously decarboxylate? In heat, I guess. Oh, I guess it won't. A dicarboxylate. Which one will spontaneously? Decarboxylate. When heated. So beta keto acids and dicarboxylic acids spontaneously decarboxylate when heated. But carboxylic acids probably won't. I mean, if they do, it's going to be heat. But I think the answer is no. All right, amides. The nucleophile is ammonia or an amine. The name of the cyclic form is a lactam. Esters, you react an alcohol with a carboxylic acid, and you get a lactone for cyclic forms. Anhydrides, two carboxylic acids together, and the name of the cyclic form is no different. It's still an anhydride. Nucleophilic acyl substitution is the substitution of an attacking nucleophile for the leaving group of an acyl compound, which includes carboxylic acids, amides, esters, and anhydrides. The nucleophile attacks, opening the carbonyl and forming a tetrahedral intermediate. The carbonyl then reforms, kicking off the leaving group. This reaction is favored by acidic or basic conditions. Number 3, sodium borohydride is not strong enough to reduce carboxylic acids. Lithium aluminum hydride, however, is strong enough and reduces carboxylic acids to primary alcohols. Number 4, 1,3-dicarboxylic acids will spontaneously decarboxylate when heated due to the stable cyclic intermediate setup. I guess they didn't say monocarboxylic acid, they just said carboxylic acids. Specifically, dicarboxylic acids will decarboxylate. All right. Got some practice questions. All right. Number 1. Which of these compounds would be expected to decarboxylate when heated? So these are dicarboxylates, dicarboxylic acids rather, but they're not 1,3-dicarboxylic acids. So the 1,3 are the ones that would spontaneously decarboxylate, even though these are dicarboxylic. The A and C are dicarboxylic acids, but they're not alpha beta, or they're not a beta, meaning they're not 1,3. They're not separated only by one carbon. These are separated by one carbon, but these are ketones. This is an acid and a ketone, a keto acid. This is a beta keto acid, meaning that it's a 1,3. So D has got to be the one that spontaneously decarboxylates. Carboxylic acids have higher boiling points than their corresponding alcohols, primarily because molecular weight is increased by the additional carboxyl group. No. B, the pH of the compound is lower. pH of the compound is lower, but that's not the reason. Acid salts are soluble in water, also not the reason. Hydrogen bonding is much stronger than in alcohols. D is the correct answer. 3, which of the following carboxylic acids will be the most acidic? Which is more acidic? I think we saw that pentane had a higher pKa, so less acidic than a smaller. So I think longer chains make for slightly less acidic. Just to go back to the chapter, right in the beginning, they told us carboxylic acids are relatively acidic with pKa values on the order of 4.8 for ethanoic acid and 4.9 for propionic acid. So ethane is 2 carbons, propane is 3 carbons. More carbons makes for a slightly higher pKa, so less acidic. So which will be the most acidic? Will have the least carbons. So C, 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 C. They all have 4 carbons. So that's not the point. The point is the substitution. So substituents on carbon atoms near a carboxyl group influence anion stability and therefore affect acidity. Groups like NO2 or halides are electron withdrawing and increase acidity. In contrast, NH2 or OCH3 are electron donating groups that destabilize a negative charge, decreasing the acidity of the compound. Closer the substituent groups are to the carboxyl group, the greater the effect will be. So let's take a closer look at these compounds, draw them out a little. CH3, CH, Cl, CH2, COOH. That's A. B is CH3, CH2, Cl, COOH. C is a CH3, CH2, CH with the Cl, and then COOH. And the last one is CH3, CH2, CH2, COOH. All right, so chlorine helps with acidity. Closer to the carbonyl, more effect. What did we do here? What was the difference between B and C? B. Oh, I messed this up. B has two Cls, while this one only has 1 because it's got an H. This has Cl2. The more Cls, the better. B is the winner. Cls more than no Cls, closer Cls more than further Cls, and 2 Cls are more than 1 Cl. So the answer's got to be B. Number 4, which of the following molecules could be classified as a soap? CH3CH2 times 19 COOH. Sure. CH3COOH. Sure. CH3CH2 19 COONA. Oh, it's the salt, not the COOH. These are acids. This is a salt. The salt. When you take an acid, make a salt out of it, you get the soap. So CH3COONA, CH3CH2 times 19 COONA. The times 19s is better. So let's go with C. Number 5. What is the final product of the following reaction? We have CH3CH2 times 4 CH2OH. An alcohol with CrO3, H2SO4, and acetone. So the CrO3 is the reducing or oxidizing agent, rather. Oxidizing agent. Oxidants, CrO3. So we have an alcohol being oxidized into presumably a carboxylic acid. Start with CH3CH2 times 4. They all have that except this last one. This last one has 2 COOHs on it. I don't think that's what's going on here. We just have one alcohol, one hydroxide functional group, so we'll get one carboxylic acid out of it. And these two are not even carboxylic acids. This, we have an aldehyde, and this is just an alkane. The whole point is to get an acid. 5 has got to be B. Six, carboxylic acids can be reacted in one step to form all of the following compounds except esters, amides, alkenes, alcohols. So carboxylic acids will be reduced to aldehydes before alcohols. So I don't think that's a one step. If we go up here to reduction, right, there's 2 steps. One hydrogen, turning it into an aldehyde, and then another turning it into an alcohol. So it's not alcohols. Can a carboxylic acid go directly into an alkene? I guess how do you chop off the whole carbon? Decarboxylation produces still a ketone. So esterification amides So carboxylic acid plus amide equals amide. Carboxylic acid plus alcohol equals ester. To make alcohol, you have to reduce it but to make alkenes, how do you make alkenes out of carboxylic acids? Carboxylic acid to alkene. What kind of reaction does that? Alkenes may be converted into So, I don't think carboxylic acids make alkenes. Alkene from carboxylic acid. Alkanes can be prepared from carboxylic acid via the removal of carbon dioxide. This process is known as decarboxylation. It produces alkane with a carbon atom lesser than present in the carboxylic acid. So we talked about decarboxylation of a keto acid, but you can also decarboxylate carboxylic acids into alkanes. It's just the alcohol that you can't make in one step. It takes 2 steps to make alcohols. So the answer is D. I had to check that you can make alkenes through decarboxylation, and you can. 7. The reduction of a carboxylic acid using lithium aluminum hydride will yield what final product? Reduction of carboxylic acid with LiAlH4 makes an alcohol. Yeah, D. 8. Which of the following is true with respect to a micelle in a hydrophilic environment? The interior is hydrophilic. The structure as a whole is hydrophobic. It is composed of short-chain fatty acids with polar heads. It can dissolve non-polar molecules deep in its core. A micelle in a hydrophilic environment, the interior is hydrophobic, the exterior is hydrophilic. Structure as a whole is hydrophilic, so A and B are false. C, it is composed of short-chain fatty acids with polar heads. I guess technically they're long-chain fatty acids with polar heads. So C is not quite right. It can dissolve non-polar molecules deep in its core. That is true. 8 is D. 9. In the presence of an acid catalyst, the major product of butanoic acid and pentanol is. So you have an acid and an alcohol makes an ester. And esters are called OAte. So butanoic acid will make butanoate. Or I guess it's butanoic acid with pentanol. So it's a pentanoate. Since pentane is longer than butane, I guess we adopt the pentane name. 1, 2, 3, 4 butanoic acid plus 1, 2, 3, 4, 5. Whoops. Pentanol. So we're going to have this attack, this thing, and then this, and then water leaves. And what we're left with is oxygen. This hydrogen also leaves. We have oxygen, carbon, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the longest chain one, two, three, four, 5. So yeah, I think is it pentyl butanoate or is it butyl pentanoate? I guess it's butyl pentanoate. Let's double check how we do this syllable, the suffixes and prefixes. Esters are named in the same manner as salts of carboxylic acids. For example, the ester shown in the reaction has the common name ethyl acetate. So ethyl acetate, this was acetone, or this is carboxylic acid. This is acetic acid being attacked by ethane or ethanol, so they call it ethyl. So here it's pentyl, so it's not pentanoate, it is still butanoate. It's pentyl butanoate because the pentanol gets the prefix. So I guess 9 is going to be D. We took a look at the mechanism, but I guess that's not really important for the naming. 10. The alpha hydrogen of a carboxylic acid is more acidic than the hydroxyl hydrogen. No. Less acidic than the hydroxyl hydrogen. Yes. Relatively acidic as organic components go. Yes. 2 and 3 are both true. D. 11. The reaction of formic acid with sodium borohydride will yield what final product? Formic acid, which you'll remember is just methanoic acid. Formic acid with sodium borohydride. So we learned that sodium borohydride does not reduce carboxylic acids. So the final product will be a carboxylic acid. 12. The intramolecular reaction of 5-aminopentanoic acid through nucleophilic acyl substitution would result in 5-aminopentanoic acid. 1, 2, 3, 4, 5. Pentanoic. And 1, 2, 3, 4, 5 amino. Nitrogen and something. Either R groups or just H's. Maybe just one H, depending on what kind of environment it's in. So, let's look at what they say. 5-amino. Pentanoic acid. They have the NH2. I think you'll probably lose a hydrogen, and then this will attack the carbonyl. Water leaves. What you're left with is a cyclic amide, or a lactam, I guess. Cyclic amides are lactams. I believe what you're left with is a lactam. Let's finish this just to take a look at what the structure looks like. N followed by 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. That is not 5. This would be 5 carbons and 1 nitrogen. 5 carbons, 1 nitrogen makes a hexagon. And an oxygen. I think what you get would be this not lactone. You'd get the epsilon. No, you'd get the delta lactam. Anyways, 12, C. (13) Butanoic anhydride can be produced by the reaction of butanoic acid with which of the following compounds? An acid with itself. So butanoic acid with butanoic acid. I think it's just A, 13A. 14. Nucleophilic acyl substitution is favored by basic solution, acidic solution, leaving groups that are strong bases. Not 3, leaving groups that are weak bases. Weak bases make good leaving groups. But basic and acidic both can work. So 1 and 2 only. 14, C. Let me double check that that is true. These reactions are favored by a good leaving group. Remember, weak bases make good leaving groups. These reactions are also favored in either acidic or basic conditions. All right. (15) The reaction of ammonia with caprylic acid found in coconuts would produce, well, an acid with ammonia would make an amide. That's not one of the options. But since it is a dehydration reaction, I guess water is also produced. So I guess water is the only one correct on this list. Not ester, anhydride, or alcohol. This would make amides or lactams. So the only thing on the list that you'd make is water. All right, let's see how we did. We have number 1, D. Number 2, D. 3 is B. 4 is C. 5 is B. 6 is C, not D. Carboxylic acids cannot be converted into alkenes in one step. Esters are formed, choice A, are formed in nucleophilic acyl substitution reactions with alcohols. Amides are formed by nucleophilic acyl substitution reactions with ammonia. Alcohols may be formed using a variety of reducing agents. To form alkenes, carboxylic acids may be reduced to alcohols, which can then be transformed into alkenes by elimination in a second step. So they're not considering the reduction of of carboxylic acids to alcohols multiple step. It's one agent. Just you need 2 moles of hydrogen. But the decarboxylation of a carboxylic acid to an alkene takes more than one step. You can only reduce it to an alcohol, and then you have to use a different reaction to get rid of the alcohol. Elimination. All right. 7 is D. 8 is D. 9 is D. 10 is D. 11 is B. 12 is C. 13 is A. 14 is C. And 15 is D. So there you have it. That is carboxylic acids. Next time, Chapter 9, carboxylic acid derivatives.